Good morning to all. Welcome to the today's session. Yesterday we discuss about the relation between Kc, Kp, Qc, and the change in the free energy. So today we are going to discuss about the factors affecting on equilibrium and applications of the Le Chatelier principle. Factors affecting on equilibrium and applications of Le Chatelier principle. So this topic is a last topic in a chemical equilibrium. Factors affecting on factors affecting on equilibrium and applications of Le Chatelier principle. So before going to the application, so I want to say some information about the equilibrium. So let us take the reactant gives the product. So this is a reversible reaction, and this reaction is already present at equilibrium. Present at equilibrium. That means rate of forward reaction is equal to rate of backward reaction. And there is no change in the there is no change there is no change in the concentration of the reactants and concentration of the product. This is equilibrium conditions. Rate of forward reaction is equal to rate of backward reaction, and there is no change in the concentration of the reactants and products. Right. If I change the conditions of this equilibrium reaction, then the equilibrium will get disturbed. If I change the conditions of this reaction, this reversible reaction, so then automatically the equilibrium will get disturbed. Therefore, the disturbance is reduced by shifting the equilibrium reaction either in a forward direction or a backward direction. So once again, so if I change the conditions of this equilibrium reversible reaction, then the equilibrium will get disturbed. The disturbance is nullified by or reduced by shifting the equilibrium will towards a forward direction or towards a backward direction. Means the reattainment of the equilibrium will takes place. Reattainment of the equilibrium will takes place. So that is a factors affecting. So conditions nothing but here factors. So those factors are factor number one, effect of concentration. Effect of concentration. Effect of concentration. Effect of pressure. Effect of pressure. Effect of temperature. Effect of temperature. Effect of catalyst. Effect of catalyst. And addition of inert gases. Addition of inert gases. So these conditions we alter on the equilibrium reaction, then equilibrium will get disturbed and the disturbance is nullified by the shifting of the reaction either in a forward direction or a backward direction. So now let us consider the general equation or any one known example. So here first factor effect of concentration effect of concentration. Completed. Okay, I will. Yesterday is complete. Okay, just 1 or 2 minutes. I will finish it. Right. Effect of concentration. So let us take the example of any one equation. N2 plus 3H2. N2 plus 3H2 gives 2NH3. Example number one. Example number two. H2 plus I2 gives 2HI. Okay, now. So this equation 1, equation 2, or reaction 1 and reaction 2 already at equilibrium. The condition is already at equilibrium. So if these two reactions are already at equilibrium, if if I increase the concentrations of reactants, if I increase the concentration of the reactants or decrease the concentrations of products, then the equilibrium will shifted towards forward direction, and vice versa if I increase the concentration of the reactants or addition of the reactants to the reaction container, or removal of the products or decrease of products in the reaction container, then the reaction will shifted. The reversible reaction is shifted towards the forward direction and vice versa. Vice versa means here take the opposite condition. If I remove the reactants from the reaction container or decrease the reactants from the reaction container and addition of the products or increase the concentration of the products, then the reaction will shift towards the backward direction. That is the effect of concentration on equilibrium. Got it, Amma? Students, got it? Got it? Next, effect of pressure on equilibrium. Effect of pressure on equilibrium. Effect of pressure. Second factor, effect of pressure. In effect of pressure, so in this category we consider the number of moles of the reactants and the products. So here we take the two cases, that is three cases. Case number one, effect of pressure. Case number one, delta N is equal to 0. Delta N is equal to, board clear number one, check your internet number please. One, check your internet. Otherwise, leave the meeting. 2 minutes wait 2 minutes. Otherwise, leave the meeting and rejoin. Then you will get a clear video. Okay, now. What about the other people? Is it clear to all? Let me know in the chat box. Otherwise, is it okay? Is it clear to all? Okay, Josna, right? Tasmia Sadaf JB1, clear only, sir. Okay. The people who who don't have a clear, please leave the meeting and immediately rejoin. Then you will get the clear video. Okay, now let's see here. Effect of pressure. Case number one. Delta n is equal to 0. Delta n is equal to 0 means, what does that mean here? Number of moles of the reactants of gaseous state is equal to number of moles of the products in a gaseous state. So we know the formula delta n is equal to n of p of gaseous state minus n of r of gaseous state. When the number of moles of the products gases is equal to number of moles of the gaseous reactant are equal, then delta n value is equal to 0. Then the conclusion about this effect of pressure. Delta n is equal to 0. No effect on equilibrium. No effect on equilibrium. No effect on equilibrium. See example H2 plus I2. H2 plus I2. H2 plus I2 gives 2HI. Next N2 plus O2 gives 2NO. In this case, number of moles of the reactants, gaseous reactants is equal to number of moles of the gaseous product. Number of moles of the gaseous reactants is equal to number of moles of the gaseous product. What does it mean? Per unit area, number of moles of the reactants is equal to per unit area number of moles of the products. 2 is equal to here. Here also 2 is equal to 2. So therefore, if I increase the pressure, no change in the number of moles of the reactants per unit area, no change in the number of moles of the product per unit area. Or if I decrease the pressure, pressure on this delta n is equal to 0 cases, then also number of moles of the reactants per unit area is equal to number of moles of the products per unit area. Therefore, no effect on the equilibrium. When number of moles are not equal in the reactants or a product side, then it has a pressure effect. Remember this. That is case number 2. Case number 2, for example, if I take the delta n is not equal to 0. Delta n is not equal to 0 means number of moles of reactants of gaseous state is not equal to number of moles of the products of the gaseous state. Okay, Nama. See here, delta n is not equal to 0 means number of moles of the reactants at a gaseous state is not equal to number of moles of the products at a gaseous state. So in this case, A. Okay, now. So delta n is equal to positive. Delta n is equal to positive, and B, delta n is equal to negative. Delta n is equal to positive and delta n is equal to negative. So in a case 2A, I am taking case 2A, second case and example A. See here, example A. If delta n is equal to positive, example of this reaction PCl5 gives PCl3 plus Cl2. PCl5 gives PCl3 plus Cl2. Next, NH4HS solid gives NH3 gas plus H2S gas. In this case also, okay, now number of moles of the products is greater than the number of moles of the reactants for a gaseous state. So these two are the examples, right? If delta n is equal to positive means per unit area, number of moles of reactants are less in a reactant side, and the number of moles of the products are more in a reactant side per reactant and product. Number of moles of the reactants per unit area is smaller than the number of moles of the products per unit area. Okay, now in the right hand side. So if I increase the pressure, in this case delta n is equal to positive. 2 minus 1 is equal to 1, delta n is equal to positive. If I increase the pressure on this, what happened? This side number of moles are more, nothing but the volume is more. What does that mean? Number of moles is directly proportional to volume. This is Avogadro's law. Number of moles is directly proportional to volume. So this side, product side is more number of volumes are there, more number of moles are there. Therefore, if I increase the pressure, the equilibrium will shift it to decreasing number of mole side, decreasing number of mole side, because here already more number of volumes are there. More number of volumes are there here, less number of volumes. If I increase the pressure, the equilibrium will shift it to decrease in the pressure side, because here volume is less. Okay, now, volume is less here, right here. Then automatically the equilibrium will shift it towards a backward direction. Is it clear, girls? Is it clear to all students? Is it clear to? One second, listen here. Okay, listen all of you. Okay, just delta n is equal to positive means this is an example. Means number of moles of the products is greater than the number of moles of the reactants. So in this case, what is the number of moles of the products of gas state is greater than number of moles of the reactants of the gas state. It's okay now. Is it clear? Number of moles of the product is greater than number of moles of the reactant. That's why we will get the delta n value is equal to positive. So when in this case, if you apply the pressure has an effect and the equilibrium will get disturbed. Okay, now when the delta n value is not equal to 0, then automatically it has a pressure effect. Okay, it has a pressure effect, that is delta n value positive and the delta n value negative. Right. So it has a pressure effect. So then what happened here, equilibrium will get disturbed. The disturbance is nullified either the shift of the reaction in the forward direction or a backward reaction. In this case, okay, now I increase the pressure of this reaction. What happened? So here number of moles of the products per unit area is more here. 2 moles are there. Number of moles of the reactants per unit area only 1 mole. If I increase the pressure, what happened? If I increase the pressure, okay, now so number of moles are here, less number of moles are there, then automatically the equilibrium will shift it toward the backward direction. See the conclusion. Pressure is inversely proportional to volume. If I increase the pressure, volume decreases, so the equilibrium will shift it towards a decrease in volume side. And volume is directly proportional to number of moles, means decrease in number of moles side, the reaction will shift it. Got it, Amma? Girls, is it clear? Is it clear, Amma? So simple, pressure is inversely proportional to volume. If I increase the pressure, the equilibrium will shift it towards a decrease in volume side. Decrease in volume, nothing but a decrease in number of moles side. So this side number of moles are decreases. Therefore, delta n is equal to positive case, the equilibrium will shift it towards the backward direction. This is the conclusion. Backward direction. Got it, Amma? Got it up. Next, if delta n is equal to negative, if delta n is equal to negative, then number of moles of reactants is smaller than the, greater than. Delta n is equal to negative. If delta n is equal to negative, then number of moles of reactants is greater than number of moles of the products. Example of this case, N2 plus 3H2 gives 2NH3. N2 plus 3H2 gives 2NH3. 2SO2 plus O2 2SO2 plus O2 gives 2SO3. These two examples are okay now. These two reactions are the examples for the delta N is equal to negative. When delta N is equal to negative, what does it mean here? Number of moles of the reactants per unit volume is more compared to the number of moles of the products per unit volume. Then N of R is greater than N of P. For in this case, if I increase the pressure, what happened? Increase the pressure is inversely proportional to volume, means the number of moles decreases side, the equilibrium will shift it. So this side, number of moles are decreases, right? So because volume is directly proportional to N, So for a delta N is equal to negative case, the equilibrium will shift it towards the forward direction. Just remember this relation, effect of pressure on equilibrium. Pressure is inversely proportional to volume. If we increase the pressure, equilibrium will shift it towards a decrease in number of moles side. If I decrease the pressure, equilibrium will shift it to increase the number of moles side. That is the conclusion. So delta N is equal to negative. If the pressure increases, the equilibrium will shift it toward the forward direction. If pressure decreases, equilibrium will shift it towards the backward direction. This is the conclusion of the effect of pressure on the equilibrium. Next factor number 3, that is effect of temperature. Effect of temperature. So let us consider the reactant gives products. This is a reversible reaction. This reaction is already attained the equilibrium. Let us assume forward reaction is a exothermic reaction. Exothermic means heat energy is released. Heat is released in the reaction. That is called exothermic. Then automatically backward reaction. Backward reaction is a endothermic reaction. Just imagine, So in this case, N2 plus 3H2. N2 plus 3H2 gives 2NH3. And delta H is equal to minus 98 kilojoules per mole. So forward reaction, formation of ammonia is a exothermic reaction, and the dissociation of ammonia is a endothermic reaction. Now come to the conclusion. For a exothermic reaction, if you increase the temperature, decrease the rate of reaction, means it favors the endothermic reaction. Radhika, please keep in a mute mode, Amma. Radhika Agarwal. Okay. N2 plus 3H2 gives 2NH3. So forward reaction is a exothermic reaction. And backward reaction is automatically endothermic reaction. For this reversible reaction, if I increase the pressure, the equilibrium will shift it towards the backward direction. Means it favors the endothermic reaction. So effect of temperature, just only it depends on the nature of the reaction. If the forward reaction is endothermic, it's favorable for the temperature. If backward reaction is endothermic, it is favorable for the temperature. Got it, Amma? Next case number 2. If forward reaction is exothermic, less temperature is required. If you increase the temperature, then rate of reaction is decreased in the forward direction. Means it favors the backward reaction because exothermic and endothermic are opposite reactions. One side exo, opposite side automatically endothermic reaction. Okay, now so it's depend on the nature of the reaction, right? 2SO2. Uh, yes, if you want to prepare the ammonia, we have to maintain the low temperature because already here heat is releasing. Got it? Heat is releasing here. That's why in a forward direction we don't require heat. Already in the reaction heat is released. So you have to maintain the minimum temperature. Got it? If you want to dissociate the ammonia, you have to apply the more heat. Then endothermic reaction is favorable. Got it? Is it clear now? Just imagine forward reaction and backward reaction. One is exo, automatically opposite one is endo. That's depend on the nature of the reaction. How do you understand? Let us take 2SO2 plus O2 gives 2SO3. This is the reaction and the delta H is equal to negative. Delta H is equal to negative. Means forward reaction is the exothermic reaction. Forward reaction is exothermic reaction. Then for the forward reaction, we don't require the temperature because already heat is releasing in the reaction. Okay now. So if you want to dissociate the sulfur trioxide, means if you want the SO2 and O2 from SO3, then you have to apply the heat, then it favors the backward reaction. Got it, Amma? Is it clear? Is it clear, Amma? Next, effect of catalyst on the equilibrium. Effect of catalyst on the equilibrium. Effect of catalyst. So see here, effect of catalyst. The catalyst doesn't affect on the equilibrium, but it increases the rate of forward reaction and the same quantity increased by the rate of backward reaction. There is no effect of catalyst on the equilibrium, just only it increases the rate of forward reaction and the rate of backward reaction with the same quantity. Got it? So let us see here one of the graph. Reaction coordinate versus potential energy. Potential energy E. So let us say reactants are present here and reactants are converted into the products. This is a reaction path. This is an energy barrier. This is energy barrier. Okay, now from reactants to the energy barrier, this energy is called the activation energy for the reaction. So this path is without the catalyst. This path is without the catalyst. The reactants are converted into the product. If I add the catalyst, then it decreases only activation energy of the reaction and immediately convert into the product. This is a path of the with catalyst. With catalyst. This is without catalyst. So from this, what do you understand? If we add any catalyst to the reaction, either reversible or irreversible reaction, it increases the rate of the reaction. That's it. It doesn't alter the equilibrium, because equilibrium reactions are the reversible reactions. Reversible reactions. It increases the rate of forward reaction, and also at the same time it increases the rate of the backward reaction. What do you mean? Immediately attain the equilibrium. Immediately attain the equilibrium. Immediately attain the equilibrium. It increases the rate of reaction, and the same quantity is increased with the rate of the backward reaction, and it doesn't appear in the rate expression. It doesn't appear in the rate expression. This terminology we can read in a chemical kinetics, no need to worry about. It doesn't affect, expression in the rate expression. Got it? Effect of catalyst. Catalyst doesn't affect on the equilibrium, just it is only increase the rate of forward reaction, and the same quantity is increased by the rate of backward reaction, means immediately attain the equilibrium, and it gives a new pathway to the reaction. It gives a new pathway, means it decrease the activation energy. Before the catalyst, this is the energy required for the reactant is converted into the product. After addition of the catalyst, this is the only the activation energy, means it gives a new path to the reaction. Now this is called the catalyst. How do you define the catalyst? It doesn't involve in the reaction, but increase the rate of the reaction. That is called the catalyst, and it doesn't appear in the rate expression. It doesn't appear in the rate expression. That is called the effect of the catalyst. Effect of catalyst. Got it, Amma? Girls, is it clear? Is it clear to? Okay, next. Last factor is effect of inert gas. Addition of inert gas. Addition of inert gas. Addition of inert gas. So in this we have the two cases. Addition of inert gas at constant volume, and B, addition of inert gas at constant temperature. Addition of inert gas at constant volume, and addition of inert gas at constant pressure. Now see here, addition of inert gas at constant volume. In this case, let us take, this is one of the container. This container possesses N2 plus 3H2 gives 2NH3. Right, this is a movable piston. It is fixed. Then only volume is constant. If I add the inert gas from the outer source, if I add the inert gas to this reaction container, just only pressure of the system is increased. That's it. Pressure of system increase. Only pressure of the system is increased, and there is no change in the partial pressure of reactants and the partial pressure of the products. Listen all of you once again. Addition of inert gas at constant volume means volume is fixed, and add the inert gas to that container, then internal pressure is increased by addition of the gas, but individual pressure doesn't increase. So nitrogen pressure doesn't increase, hydrogen pressure doesn't increase, ammonia pressure doesn't increase, because number of moles are equal in the container, but only we add the inert gas to the container. Therefore, no effect on the equilibrium. No effect on equilibrium. Next, addition of inert gas at constant pressure. Addition of inert gas at constant pressure. Same here, for example, N2 plus 3H2 gives 2NH3. So this is a movable piston, right? So I want to maintain the constant pressure by adding the inert gas.